So today I'm going to talk to you a little bit about our journey, how we've been chasing this whole EV market, the whole trend. The story starts somewhere around 2018 when we got all of these projections that EV batteries were going to be the future, and we saw all of these very high projections that they're going to be in the 150,000, 250,000 range of builds. The problem is we didn't have the proper electrodeposition coating, or Ecoat, to properly make a protective barrier against corrosion for these units. Why was that? Why was that? It's because basically we went from a standard ICE engine to the EV or battery pack, and this battery pack is very dense metal, high complex structure, and is almost like a heat sink. So a standard Ecoat coating does not protect, it will not cure in some of those areas. Some of those deep recessed areas would not cure. So we had to change our thinking way and move to something that we call broad bake Ecoat. So I'm going to use broad bake, low bake, and expanded bake interchangeably. It's the same technology. In short, it means basically maintaining all of our properties at the high level at 200 C bake. A standard Ecoat would cure at 160 C, right? 10 minutes, 20 minutes at 160 C. And then pushing our properties down into the 140 range, which is new territory for us, and still delivering all of the properties. So that's what we mean when we say standard bake, broad bake, and low bake. So I'm going to use those interchangeably. Starting off with our story, we started working on this development around 2018. We got approvals and we got our technology launched and commercialized in 2021. And so since 2021, our end users have been realizing a lot of cost savings. And I'm going to share a little bit with you today. In addition to them realizing cost savings, we try to take our process technology and our knowledge about the process and try to capture some savings that way so we can multiply and stack the savings on top of each other. So you get material savings, you're helping the environment, you're helping sustainability, you're saving on water costs, and you're still giving a protective coating that, again, will protect that battery pack. So here's my quick agenda. We're going to talk about electrical megatrends. If you've spoken to me in the last 5 years or so, you've seen a couple of these slides, okay? Because the megatrends for electrocoat have not changed. We want to be more sustainable. We want to use less material. We want to reduce our CO2 footprint. We want to be able to coat complex substrates and multiple substrates. We want it to be, efficient. We want to improve our coulombic efficiency, which is a fancy term for, as you know, electrocoat, under the influence of electricity, it migrates to the part and then coagulates out and makes the coating that way. It's different from the spray coatings. So our ability to carry that charge and coagulate to the part has to be increased to help efficiency. And then finally, we need to be able to deliver a cross-link dense coating at 140 C. So we're going to talk a little bit about that. Then we're going to talk about some of the derailers that we've been seeing with the EV. I think the keynote speaker today touched on a lot of that. But we'll talk about those derailers and things that have slowed down the industry. So since the EV industry has slowed down, do we just give up on low bake? Absolutely not. What a lot of my end users have been doing is still adopting low bake technology and then using some of these efficiencies to save money, reducing their costs, reducing their material consumption. Same deliverables, but maybe now for an ICE unit as well. We're going to talk about what we did. So that's the why. And then we're going to talk about the how, which is how we designed the system. I don't have a lot of chemistry in here just because I know some of my competitors are in the room. But a lot of smart people, smarter than me, back at the GIC, back in Europe, in Wuppertal Laboratory, did an excellent job helping us drive to this goal and make it achievable. Then we'll talk about one or two commercial examples and some of the money these folks were able to put into their pocket. So the electrical megatrends, as I mentioned before, these have not changed over the years. You know, we want to be positioned to be able to coat e-mobility, whatever that electrified vehicle is or workpiece is, we want to be able to coat it. We want to be more sustainable. We want to use less water, drive down costs. We got to have a robust supply chain that's globally available. And as you can see on the left, some of the technical challenges for the coating. Now we're dealing with these more complex structures. You know, we have to be able to, you know, I meant to mention this earlier in my introduction. When we first got in this path on this journey, our folks were kind of scattered, right? We had some folks working on intermescent coatings. We had some other folks working on dielectric shielding. We had some other folks working on low bay cure. You know, so we weren't really orchestrated in a way that was kind of cohesive. Over the years, we've worked on that and figured it out and brought all those groups together. So now, you know, it's one product. Does it meet all of those requirements for battery packs? Absolutely not. You're still going to need, in my opinion, you're still going to need other coatings, you know, for dielectric, shielding, EMI, whatever the case may be. If you're worried about thermal runway, one system can't deliver all that. And if a supplier tells you that, that's you should take that with a grain of salt. One coating can't deliver all of that. So these megatrends, again, if you've spoken to me in the last 5 years, they're the same 5 or 6 megatrends that we've seen forever. Then, you know, we had this race to EV, you know, batteries, everything was going to be EV. So we were scrambling as well to be ready for the market change, and it never quite happened. You know, even though it's been exponentially growing in China due to the government mandates, and in Europe, here in the U.S. it seems to be cooling, always seems to be cooling, and there's a lot of mega factors that contributed to that. In the Northeast, it was like extremely cold. People just didn't go to the dealership. Then the government removed the tax credit, right? So now we don't get as many EV credits as we used to. I think there was like $4,000 or $5,000, which incentivized some purchases. That has been removed. Then there's other things, you know. I put in here just recently this conflict in the Middle East. That doesn't have anything to do with EVs, but it's another factor that's just killed some of our product sales and some of our, you know, what we thought would be this huge new industry. So everyone is more in a blended production state right now instead of being, you know, 100% EV. Most of it you can see as being either hybrid or still ICE units. So this is a cutaway of an EV van, and it kind of demonstrates the complexity that I was referring to earlier. So if we're looking at a traditional internal combustion engine, right, we're used to that frame. That frame is bent metal. It's hollow. You know, we know how to coat that pretty easily. And when we apply heat to it and we bake it out, you know, we know we can achieve cure. When we get to these EV models, now we're dealing with this very complex, heavy heat sink areas that require additional heat to cure. So if I apply 160 C coating to that, more than likely that interior area is not going to cure, right? And that's why we are now targeting 140 C. The problem is 160 degrees C coating is pretty standard. It's been around for 30 years. To go from 160 degrees C to 140 degrees C is an invention. Going from 160 degrees C to 150 degrees C is still within our formulation toolbox. And so we can play around with the catalyst, we can play around with the crosslinker level, we can play around with some of the additives, and we can achieve 150 degrees C cure, no problem. But we want to drive from 150 C to 140 C. That requires innovation and, quite frankly, a new system. So this is our challenge as far as e-coaters, what we're trying to accomplish. We want to get to 140 C into some of those very heavy reinforced areas. Anecdotal story, apparently some coaters rushed to the market, got some vehicles on the road in Europe, and there were stories of actually batteries falling out of the vehicle, right? So when they root caused it, they figured out that those areas were not cured. So we're stuck with three options. Again, if you've talked to me, you've seen this animation before. First option is just to make a longer oven, right? Huge capital investment, financially, that's a big punishment for the companies. They're not going to do that. Big CapEx investment. Our second option is to slow down the production. Nobody wants to do that either. Who wants to kill productivity, right? So that leaves us with the third option, which put it on the paint supplier and make them change the product and make it work with our system. And that's what we did. As you can see in the blue is what we consider to be a standard bake. Again, within the same toolbox, I can move into the green area without a lot of effort. Just, again, changing catalyst level, changing a little bit of the backbone resin, playing around with the polymer architecture, maybe going to a little bit different crosslinker or a blend of crosslinkers. But to get to the orange area, that's a new system. Okay? So those are my three options. Guess which one our customers pick? Number 3, of course. Now for the how. Again, without giving away some trade secrets or something, we took the entire system apart and we basically redid the polymer architecture, changed the molecular weight, changed the end capping groups, changed the amine, went to a lot of crosslinker and isocyanic chemistry, and then a lot of the magic actually came from some of the catalysis work, right? If you read the patents, all of us are in the same catalyst family, all of the suppliers, paint suppliers, but it's the way in which we create that catalyst salt, that's where some of the differences lie. If you do it in the right salt formation, the molar activity and effectiveness of the catalyst changes, right? So I can use less moles and still get the proper cure. In addition to that, we've removed tin. I think a lot of the tin stuff had been around. Tin is a great catalyst, but if we're going to improve sustainability and do some of these other things that we promised the industry we would do, the tin has to come out of the system. In addition to that, we also know that the pigment carries a charge, right? So what we've learned over the years is the pigment charge actually competes with some of the deposition properties. So let's strip away that charge and change the isolation behavior of the pigment as well. All of these things combined increases a very important property for us in the electrical world, and that's called wet film resistance. So after I make all of these formulation changes, put my system together, I have basically increased my wet film resistance of this system, right? Increasing the wet film resistance, what does that do? In layman's talk, so during the deposition process, under the influence of electricity, the coating is going to migrate to the part, right? Right at the part, there's this hydroxyls are being released, and we call that the hydroxy boundary layer. During the deposition process, when the coating gets to this hydroxy boundary layer, it coagulates out and becomes a permanent film, right? And it's not reversible. If I can get that coating to coagulate quicker, that gives me more time for the paint to travel to some of these harder to recessed areas and coat those as well. So the rate of deposition changes, the coagulation properties change, and the throwpower changes as well, all which helps us get to the endpoint quicker on the exterior and gives us more time to work to the interior. So as a result, our product, which we call AquaEC Flex, we got out of the numbering business. It used to be, I've been around for a while, so I remember Cormax going back to the 80s. It was Cormax 1 through 10. Then ElectroShield 10 through 33. And then finally, when we became Axalta, our leadership looked at all of the regions, says, you're using ElectroShield, they're using AquaEC, they're using Succeed here in Asia. Let's merge all this together and make one catalog, and you're now going to be called AquaEC. So we've adopted the AquaEC branding. Some of those legacy products that that are still in the market over 10 years still use, we just changed to the AquaEC and then you still have the same number. So ElectroShield 27 became AquaEC 4027. So after a while of doing that, you just get a little worn out with the numbers, and we decided to go with these cute little names now. So one's called Flex, one's called Edge, one's called High Throw. So we're going with Flex on this one, and that's how we did it. So that's the how. So we covered the why, the problem. We've covered the how. Let's look at some of the performance data. So the first chart to that would be your left, right? To your left, this is what we call a dwarf measurement. It's a very novel way to measure wet film resistance, right? The ability for this material to coat out and carry a charge. As you can see, we've improved dramatically our wet film resistance compared to a standard Ecoat. You know, if I look at this graph here, across the bottom is time, and on the left is the film thickness. So as you can see, after that quick induction period, AquaEC Flex has already started coating to the target film build, whereas the standard material is still building. As you build like that very slowly, that kills time, right? Remember, the deposition process is very finite. It's between 2 minutes and 5 minutes. So moving from the Flex to the standard, you can see I've increased my time, again, for that extra material to go ahead into those recessed areas and coat and protect some of those recessed areas. In the middle, this is a cool little test we've done. So, you know, over the years, as, you know, the substrate complexity has changed, as we move from zinc to zirconium oxide pretreatments, we still have to perform over all of these substrates. What we've done in the middle one is we've actually taken pretreat material and poured it over the panels and let it dry, and then applied the coating to it. And as you can see, the standard Ecoat, because of its wet film resistance, its flow mechanics, it does not do a good job of covering over some of that chemical etching in the steel. When we go to the AquaEC Flex, again, because of its coagulation, its wet film resistance, it's able to cover some of that imperfection in the metal a lot better. So that's about a 35% increase in wet film resistance, which is huge for the industry. And then finally on the right, again, we talked about coagulation. You can see here, this is just a cartoon that kind of shows, on the right is my Ecoat bath, on the left is the actual deposition process happening, and my resin particles are coagulating in that hydroxy boundary layer. Again, the ability to get to that point and the coagulation of that point is what we're trying to improve, and we did. So, you know, again, we were able to improve throw power, wet film resistance, and efficiency as part of this new development. Please let me know if I'm talking too fast here, okay? Here's some more data. Again, we already talked about how we stretched out the bake window, but we've done some other, you know, we've got to confirm all of this stuff, because typically what I've noticed in the business and in the industry, you fix one thing and you actually hurt something else. So in this particular case, we wanted to do a full round robin. This is actually data from one of our end users' specification testing. In the center here is what we just do a cyclic corrosion. Typically, cyclic corrosion goes out about 50 cycles, 40 cycles, where you go heat, humidity, room temperature, you know, frozen, you know, do that for 50 cycles, and then you check creepage or the production of corrosion products. In this particular one, the engineer wanted us to run it all the way to 150 cycles, which is almost 3 times the standard, just to run it to failure. Let's just run it to failure. And we only got about 2 millimeters of creep. So our corrosion performance, which anyone who's in electrocoat, that is their main function. We are in the corrosion business. So I can deliver some of these other things for you, but I have to make sure that that middle graph is good to go. We don't want to make you more sustainable and then hurt your corrosion performance, or save you water or save you chemical and degrade some of your corrosion performance. So I was very happy to see the middle slide in those panels when we looked at them. They're, so that's 150 cycles, which is pretty extreme. I guess we overdid it on some of the submission work, and these were allowed to remain in the cabinet and continue to go. And then on the right, that just confirms the cure test. Very simple, rudimentary test. Basically, we take MEK or MIBK, and it's 10 double rubs, and the specification is no paint transferred to the white cloth, right? So as you can see at 140 C, our standard Ecoat is not cured. It has not cross-linked. It will not be a good barrier for corrosion, whereas the EC Flex does. Other properties, it depends on where we're at in the world. Some of our end users want edge coverage. Edge coverage is a very unique phenomenon. As you can imagine, you're bending sharp metal, you're contorting it, and you're shaping it, and usually you end up with some sharp edges on a vehicle. During the electrodeposition process, we're able to coat that very nicely, but then when it gets in the oven, due to the film flow and the cross-linking, some of that coating will pull away from the edge, and that's our first place where we see corrosion. So some of our customers ask us to enhance the edge coverage. So we have these special panels I believe we get from ACT they're burred, and I think some of them have a laser cut on them, and we coat those, and then we just kind of use photography or microscopy to look at how we protect the edge. And in this particular case, the visually is quite obvious. In the middle, another thing that's very important is paint stability. So the middle one just basically is the process of heat stressing the paint, seeing if some of that polymer, remember, Ecoat is a unique thing, right? So we build the polymer in an oil-based system, and then we add acid groups and we trick it and to go through a process which we call inversion, where we invert it into a water base, and then we can use it to run electrophosphoresis and deposition. But when you first start off on the Ecoat system, it is polymer synthesis in oil base, right? And then we trick it to go into water base. So in the middle, we just want to make sure under extreme stress, agitation, heat, does any of that stuff fall out of solution? Back in the 90s and the 80s, things used to fall out of solution quite a bit. Usually it's pigment, so that technology has come a long way. But this is just a confirmation. So you put this under stress, you do an L panel, and you run it through a filter and and you measure how much residue you actually capture in the filtered media. And then finally, throwpower on the right. This is a big property for consumption, for performance, and for for usage for sure. So it's basically the Nagoya 4-box test. I think a lot of people anyone who's worked in Ecoat knows what this is. It's basically 4 panels. The first 3 have a hole in them, and the last one is solid. And the vessel is completely airtight. And under the influence of electricity, the paint's got to travel through the hole and coat the back panel. The measurement of the ratio between the back panel and the front panel, which we call the A face, which represents the exterior, and the G face, which represents the deep interior, we want that to be over 50 to 60%. So that's what this is kind of showing here. It's just kind of showing, again, because of the wet film resistance and the efficiency of the new material, I'm now able to get that A face coated to 16 microns very quickly, and then it gives me more time to get the G face coated, which means an increase in throw power. So what about the process? Yeah, there's problems with the process as well. Whenever I visit a plant, some of the first things I do, I look at the rinses and the sprays and see how well you're recovering your paint solids. Ecoat, and the Ecoat system is a closed loop system, right? So anything I can recover before that vehicle or that workpiece leaves the area can be recycled and reused on another vehicle. All right, so what we do not want to see is we don't want to see paint dripping, a lot of paint dripping on the floor heading to the oven. That's system loss, right? In each vehicle, a typical OEM vehicle, there's typically about 2 gallons of carryover. We call it carry out. So it's about 2 gallons of paint that you're losing per vehicle. So if you can imagine, you do that times 1,700, 1,500 vehicles a day, it's a lot of system loss. So that's one of the first places that we recommend as best practices to try to recapture some of those solids and use them for the next, to deposit new work. The other place I see all the time is problems is with overbaking parts. I think we have this mentality in the OEM world, set it and forget it, right? Ecoat is automated. If you maintain your bath chemistry, if you have precise control of your voltage, you will end up with the correct amount of microns on those parts every time. It's very repeatable. So, but I think we take that mentality and we apply it to everything, right? So we set it and forget it. So we know the oven, the heavy metal errors need to be at least 160. So let's set the ovens to 200 C, overbake the exterior just to make sure we have that 160 on the heavy metal hinge. So I like to get people out of that mentality and see if we can work together to find places where maybe we can customize some stuff. Precise film build control is one of the easiest ways to reduce waste and consumption, right? So if you're using different vehicles through the same line, using a little bit of modular rectification where, the SUV gets module or profile A, and then the sedan that comes behind it gets profile B. That's, that's precise film build control, which at the end of the day adds up to a lot of cost savings. The other place I see as always an opportunity to save money is water. Water is always typically abused and misused in a lot of the Ecoat and the pretreatment processes. I can walk in some places, we can find fresh water overflowing the drain up to 40 gallons a minute, right? Doesn't sound like a lot. 40 gallons a minute times 60 minutes times 245 days. It's about 1,100 gallons, I believe, it's about 57,000 gallons per year. Multiply that out times, 2, 3, 4, 5 cents per gallon. Significant money. So that's another place I immediately migrate to. It's like, let's figure out how we can recycle, reuse some of this water instead of let it go to drain. Because you're going to get taxed twice, right? You're going to get taxed to make the water, and then you're going to get taxed to dispose of the water. So if we can cut some of that cost, that's usually another place we can really help our customers and our end users. And then, again, the set it and forget it mentality. I have a lot of customers that are still stuck in some of their older technologies where they're still putting 25 and 30 microns on these parts. You can find, we've demonstrated you can get down to 12 or 13 microns and still protect that part quite well. So that's another reason. And, I've worked with some of our end users in this room, and I think one particular case we were able to get them about $500,000 in cost savings just by optimizing their process. I apologize for this as an eye chart. Let's just call this the reference. You can read this at your convenience. This basically is what I said in the earlier slide, just giving a few more details. It looks like I'm getting the hook. Am I getting the hook? I'm getting close? 2 minutes. All right, let's get through it. All right, so here's an actual cost-saving example. This particular customer, we did a pour-over conversion. That means stop feeding the new material, stop feeding the old material, start feeding the new material, convert the technology. It takes about 90 days. And they were able to deliver. First, the thing they did was they were able to increase their line speed 63%, right, just by going to a lower cure material, right? They also used less chemicals. They got rid of the tin. They removed about 168 kgs of tin from their waste system. And as you can see at the bottom there, that we ended up saving them about $300,000 year over year in operational costs. In addition to that, CO2 footprint was significantly lowered. We saved them 1.64 kgs per vehicle. 1.64 kgs per vehicle. Multiply that again times your whole production year. That can be up to 112 metric tons of CO2 demand that you save for this customer. This just kind of shows what 112 metric tons is equivalent to. It's equivalent to powering 23 homes, using about 13,000 gallons of gasoline, 26 cars on the road for a year, or about 125,000 pounds of coal being burned. So that's significant. Another eye chart. This kind of shows their utility costs, their cost to coat per vehicle, and their greenhouse gas emissions. The big number here is the greenhouse gas. We're able to save them, again, about 1.64 kgs less CO2 per vehicle, turning the oven down from 220 C, now it's probably about 170 C. Huge, huge for them. So this also calculates out to about 12.5 US dollars per vehicle less in material demand, because now you're not baking it all off. A little bit of savings in natural gas and some of the electricity, but again, the big one is material and CO2 demand. I'm almost there. So in conclusion, so maybe you're not doing 250,000 EVs per year. If you're doing 70,000 EVs per year and you're still doing ICE engines, get out of the set it and forget it mentality. Think about upgrading your technology to something that's more sustainable, works on complex substrates, works with zinc and zirconium technology, and it requires less CO2. Something like a broad bake or low bake or expanded bake electrocoat.